Here's 5 fundamental cache optimizations. We can use a larger block size, means a bigger palette. Okay, larger caches generally will have a higher hit rate, but maybe slower. Someone just logged that. I just watched that half hour ago. And then higher associativity means more flexibility in the storage, but it may get complicated with our counters and things. Multi-level caches. This is actually turns out to be one of the best ways. Just keep inserting more layers. This way the cache doesn't have to grow too large, but you have a higher hit rate at each level. You're adding more parallelism. And then the final way is to add a victim cache. What's a victim cache? Victim cache says you actually have, for each level, kind of like a second chance. So in other words, instead of kicking it out back up to the other level, you just kind of say, you know what, I'm going to keep you on the side. We kind of do this in real life too, right? Yeah, you know, I know this is, I'm not using it right now, but I don't feel like putting it totally away. I just kind of like put it off to the side so I can find it quick. The victim cache is not very big, low capacity, but it's kind of going in parallel. It's like having 2 caches at each level. One is the main, which is large. Another one is the victim, is small. It goes from the main to the victim, and then once the victim fills, victim cache fills, it's going to go to the next level, back out. So it's kind of like a second chance. So getting to the dirty bit is when we have store operations. We covered load word. What happens when we update memory? We don't ever update instructions, but we might update data. When we update data, we have to write it back. We have 2 choices. This graphic, I should have went forward instead of backwards, shows this scenario. So it's exactly what I just said, but I'm actually give you real data here. We need to keep so the idea of coherence is keeping memory in sync, the hierarchy, the levels in sync. So suppose T0 register contains the value 4, and we're going to store now. We're storing T0, like I mentioned, to an address. Now, if that data is originally in cache, this value 4 is going to be written in. Did I make an animation? I'm sorry, I didn't make an animation. So 4 is written into cache here. Then the next reference loads something that's amiss, but cache is full. Suppose that this is the block or line that's replaced. If we just write over this to store the D in wherever C was, okay, then we got a problem because we've written this value of 4 to address C, but then we overrode it. Okay, so if T0 would become 7, not 4, because we've overwritten the value if memory is not kept coherent. So this is the point. The point is, there's different ways to think about this, and where it started to make sense to me. Caching sounds like a great idea, and it does have a huge effect on performance if the hit rate is high, and which a lot of programs, because of locality, can be 99.9%. So you can get away with a small cache, a very small fast memory, and the program thinks the performance of your system is as if the whole memory hierarchy is fast. But then it starts to get complicated. When we write and update data, where it clicked to me, we have 2 copies of the same information. We have D000D here, and we have 00D here. Which value is truth? That's a good question. So that turns out what was called our write policy. Our write policy tells us which of those 2 copies are truth. The simplest way to do it is just always keep them consistent. So when we read, if we find it in cache, we get a hit, it's a very fast access. If we write, we're going to update cache, and we're going to write through, that's called write through, we're going to write through to main memory as well. This way, everything is always consistent. You use this in practice. If you take your laptop and you put a thumb drive there, and then Windows is actually not that bad about it, but if it always wants you to eject it, what is the eject business about?
Right through to the memory before.
It's making sure that whatever you've updated on your file system inside memory gets copied to the thumb drive before you pull it out. It's making memory coherent between those levels. So one way to do that is just always update the thumb drive whenever you updated a value. They don't use that. That's called write back. So write through is when we always keep them consistent. Write back is we just only, when the block is deallocated, or line is deallocated, we're going to update memory only at that time. If you don't know when that is and you want to take your thumb drive out, you have to force that to happen. That's the eject. Okay. So again, if you're just reading, you don't have to worry about it. But if you have a file and you want to make sure it's saved, it's a good idea to eject it. And make sure that the memory is kept coherent. So, are we good? I see the pizza coprocessor is still in a. Is it good?
Yeah, I just need your card.
Needs my card?
Yeah.
All right.
Can you just pay when they get here? Like,
No. Well,
Yeah, if you have cash.
what's that?
Right now it's saying pay with cash upon delivery or pay now with debit or credit.
I can do cash on delivery. How much are we talking about?
$20.
Total?
Yeah.
Is it mini pizza or what is it?
No, because we're
I'm splitting it, so
Oh.
yeah.
it'll pay for
See, that's cool.
That way
Okay.
you get buy one get one free.
Yeah, no cash, no problem.
All right.
Cool. I know you guys think I'm being generous, but actually then I don't have to cook later, so that's and no lunch. I didn't have time for lunch, so there you go. But we're having fun, right? Because you guys are dedicated, all right? So here's a graphic that actually shows this process. Updates are initially made in cache only. So this is write back. Okay, this is when you eject your thumb drive. And we use an update bit for the slot. That's the dirty bit. Okay, and then if the block's to be replaced, it's only if the update bit is set. If it's not set, we didn't write to that block. It means it's clean. We can just write over it, and we don't lose any data. So here's processor, cache, memory. See the pyramid? And we update here this one word of a line. The lines are stacked this way. But then we have to write it back out if it's dirty, right? When the data is transferred, when this is deallocated. The write through is always keeping it consistent. So anytime we update cache with a new value, we write a data element out. We never update instructions, only data. We're going to also update memory. What's the disadvantage? Disadvantage is it slows down writes. Let me say this again. So if you have a read and it's a hit, it's the speed of cache. Everybody got that right. Read hit is going to be serviced by the cache that's fast. Suppose you have a write, whether it's a hit or a miss, is it the speed of cache or speed of memory? Speed of memory. So what you did is you slowed all the writes down to speed of memory. Now it turns out in practice, what does a program do? More reads or writes? A lot more, typically a lot more. What's the typical ratio? Anybody know? I can tell you. Typical ratio? Yeah, 90%. 90% or so is usually read, and then 10% is write is pretty typical for a lot of programs. So the fact that you have to have all the writes go to memory is slowing you down, but it's only slowing down 10% of the total references to memory for data. Instructions we don't worry about because we never write them. They can always be at the speed of cache if it's a hit. So here's a summary, and then I'll give you the analogy. So we need memory to be consistent. Otherwise, there's two copies. We don't know which one's truth if we don't have a policy. We can do write through or write back. If we always keep them consistent, they're never out of sync, is write through. If we only update the higher levels of the hierarchy, when a deallocation occurs, that's called write back, okay, which is here. We can also speed up a little bit by adding a write buffer. This actually gets more tricky. I would just, for today, because we're on vacation almost, just skip that one. You can put a write buffer, and then this way you don't slow it down, but then you have to check the write buffer if the thing is there too, because otherwise you wrote it and you didn't see that you wrote it. Write back needs a dirty bit. We're going to keep track if you update it or not. Neil?
So with the write through, would that be like pass by reference in C, and then write back is like pass by variable and then return the.
This is awesome because I never thought of it before, and I think you're onto something. Say it one more time to make sure that your semantics is matching. Go ahead and say one. So write
through
through
would be pass by reference in C, And then
I think
right back would be passive like variable, and then you return it back.
if you just pass in the value, that's going to be like right back.
Right.
And then if you pass by ref, so I don't never use that one that much, but if I understand the semantics of that, you're actually making sure that you update the real value of the variable, not a copy of the value.
Yes.
Then that's true, yes. Very cool. So you've got a software connection. Do you want the analogy that's not the C version? All right, so it's the same as a cookies and ice cream family. Okay, so he was a computer engineering student of mine, master's student. And the ice cream and the cookies was my house when they came over one time. And then, you know, he has little kids, right? And they want to be helpful too, right? I had some orange. It was another funny story. I had an orange tree, and it was just, you know, newly planted, and you wait for the first orange, and it was growing. It had a few of them, right? And so the kid goes out, and he comes back, and he has his shirt like this, and he goes, and they weren't ripe yet. I was like, oh, he's like, I picked these oranges for you. But anyway, this time I went to their house for dinner. And it blew my mind, right? Because I have my strategy, right? My strategy is I try not to mess anything up, actually. Why? Because then you don't have to clean. Like even my bathroom, I just go to the gym when I have time. In the morning, this is awesome, actually. I never have to clean my the shower. Actually, I don't use it. I just go to the gym. But when I went there to their house, this blew my mind because, you know, they have 4 kids, right? And they were all young kids. And the kids picking up things and toys here and all this stuff and on the counter and all over. And I'm like, oh my gosh, how are we going to ever clean this, right? It's like, and I was like, I want to like put the stuff away. I'm like, I'm stressing out, right? I'm like, oh, put that away, or, you know, you're going to trip on your toy and whatever. And the mother's like, his wife is just like not worried at all about it. But then what happened? Dinner's over and the kids kind of, you know, time for bed thing. She just went through like a wave and just put everything away at once. And I was like, efficient. You know, I would have gone crazy, like putting this away, that away. That's right back versus right through. So I do what's like right through. I always try to keep consistent. Whenever something is out of place, I put it away. That's okay if you don't have much right activity. If you're doing a ton of writes, don't try to keep memory consistent. It's like a losing battle. You're going to be too slow. Just let it get out of sync. Let it go like you're just a gigantic mess. Let the kids make a mess of the house. But then what? You just clean once? That's right back. So right through, right back. Right through is keeping it clean all the time, and right back is the monthly cleaning. It totally works, but for memory writes. If you have a lot of write activity, write back tends to be a better strategy. If you have a low amount of write activity, you know what? Just make it right through. Then you don't have to have dirty bits. You don't have to worry about it. See the dirty in the bathroom? That's a joke. Okay. It is hard to make jokes on these things too, by the way. It's going to take a lot of effort. So, we're there, almost. Yeah. Just time for pizza. Cache operations summary, contents of a block. So I have to buy pizza for their section too, right? Like dessert or something? Don't tell them?
They'll never know.
Because this is lunch, so it's lunch. So cache operations summary, contents of a block are read. Contents of a block are read. Then what? For the first time, it's going to be compulsory miss. Then we load it into cache. If we reference that same address again, it's a read hit. Eventually, we run out of cache capacity. We have to make a replacement. We have some functions that help us do that. I'm just going to hold you responsible for 2. There's actually about 20. But you can actually set these for Intel, LFU, or LRU. You'll see, I think I have a slide in the next module which is showing some of these registers. You can play around with these. Sometimes they make a difference, a few percent, in the speed of your program. What about on the right side? We have 2 schemes. Okay, we have to always keep it clean. And then we have just let it get messy, and then just when it's time to resynchronize, you just do it once. This is right through. and then right back, we let it get dirty, and then we just clean it out. People say, what's better? Well, if you don't have much write activity, this is better. If you have 4 kids, you might want to consider write back. So takeaways. Fast memories are small, and large memories are slow. Ideal design would give the illusion of a fast access time with large capacity. Memory hierarchy helps us realize this illusion. In my opinion, memory hierarchy is one of the key elements of computer engineering. We have von Neumann's stored program concept, store the instructions as bits. Those bits actually turn on the circuit. It's that simple, what every computer on the planet does. If you don't take this class, you don't have that insight. You guys actually get that insight to see, you know, yeah, they're amazingly dense and complicated structures, but they're very elegant, the way a computer works. The way a memory works, a memory system works, it relies on this hierarchy principle, and that actually leverages a very important scientific property of locality to get an engineering benefit. Here are some typical, we did L1 and L2 and L3. Next module is DRAM. We'll talk about that as main memory design. Set associative mapping is a good hybrid of direct and fully associative. So we're fully associative within each set, and then we map directly to the set based on the address. Every way that we can store the same address within the set is the way of the memory. It's the 2 ways. You get 2 chances. It's 2 ways to store data that's mapped to the same set, to the same address bits. This is most commonly used in practice. And locality we mentioned, multi-core usually use the L3 on the chip to share data, and that actually the cache is the mechanism of interchanging results on most multi-core chips. So how's that pipeline? Are we on stage 2 or 3, or what is it there? Does it get? Let's see some circuits. Okay. So semiconductor memory, as I mentioned before, we have random access memory, but actually all memory is random access. But it tends to mean that it's read-write. It's actually a misnomer, but it caught on. He said that random access versus sequential access. Sequential access is the tape model. You have to get to word 5, you have to read word 1, 2, 3, 4 up to that. So that's sequential access. We're doing random access memory. Random access memory means I give it an address, any address, the time to get the data, which means the read access time, is uniform. Doesn't matter what I read last. It's always 1 nanosecond is cached. It's always 50 nanoseconds. So we have 2 different types of memory technology, which are random access that are commonly used. Static RAM, dynamic RAM. Static RAM is a cache on-chip memory, and registers. You say, well, what's the difference? Well, bigger transistor goes faster, closer to the data path, or the register versus the cache. We saw the chip picture. Dynamic RAM is off the chip. Difference in the way it's designed, we're going to see in the next slides. This is used transistor for storage, used capacitor for storage. So here's the main memory design. And first question. Here we have an address decoder. We see flip-flops, flip-flops, flip-flops. And I'll give you a hint. This is like 1 register. So if this is a main memory design of a register file, how many registers in this register file? So this is 1 word, and it turns out in this we have B0 through B7. So how many bytes per word in this? 1 byte. 8 bytes. Sorry. Yeah. And we get to practice. You know, it's good to practice. No points off here later. So this is 1 byte per word. This is 1 word. This is the next word. Word 0, word 1. They're stacked, just like a register file. We have 4 address lines. So how big is this memory? What's the capacity of this memory?
Here it is. 2 to the 4th. What's the units? I'll take 2 answers for units. 2 to the 4th is 16. What? Words. 16 words is correct. And how many bytes in this design? 16 bytes. So this is 4 address lines. Gives you, I think this is, it should be 16 words, not 15. Sorry for the typo. And each word is 8 bits. So now we're seeing the data bus and the address bus. Remember data bus, address bus? Of course you do. So data bus and address bus, what happens? This is the chip now. We're outside the processor. This is a memory chip. Now we're taking the lid off the memory chip. Data bus comes in, address bus comes in. Take the address, we decode it, we get a 1 hot. We're going to enable one of these rows, which is a register, to drive its data out. That's how the way this circuit works. So, what are the components next? While we're here, if we're going to read, remember tri-state buffers. So we have a tri-state buffer driving this way if I want to write. What do I do when I want to write? I put data bits here, 1s or 0s. They're going in this direction. There's a circuit here like an amplifier. That's all it is actually, amplifier. It's an amplifier transistor. So we take a value, we amplify it, get some drive, and then we, because these are long lines on the scale of bits. We need capacitance, parasitics. Anyway, we put enough current here that we can write this input to this flip-flop. Remember flip-flop, D flip-flop, with the D and a Q. D input, we drive some of the data here, and the Q comes out later. Why? When we want to read it. How do we read it? We select the row. So this is actually the clock. It's calling it it's a combination. This is kind of a hybrid diagram a little bit. But the bit comes out, it's driven out tri-state buffers. Let's take a look at what's inside each of these storage cells. And I'm calling it a flip-flop. It can be a flip-flop, but one way to build a flip-flop actually has a master-slave, dual edge. But anyway, let's start with what we need to make this work. If we go here and come back. Go here. Battery. So we're going to have 2 transistors. Remember the read and write, and this was the cell storing it. So each bit, each one of those flip-flop cells, we have a way to access that cell for read and access that cell for write. Okay, so we have some what we call word line, which is the same that we saw over here. And we're going to get access for read or access for write. This is from the author, actually a different author, but he doesn't have. He should have one as a read and one as a write, but don't worry about it. Yeah, one is in and one is out. So to store a bit into the cell, what we're going to do is, remember gate, we're going to see the previous slide. So we turn on the gate by activating the word line, which means we select all the bits in this row. And then that value, either B0, B1, so on and so forth, gets written as a pass through the transistor. What we have here are 2 inverters back to back. So you put a 0, you get a 1. A 1 comes in, you get a 0 out. So this inverter keeps this inverter refreshed, and that inverter keeps that inverter refreshed. And the bits go around in a circle all day long. This takes a lot of energy because it's always computing the inversion over and over again. Typical gate delay in CMOS, 20 nanometer technology might be 50 picoseconds, 20 for inverters, only 2 transistors. So it might be 20 picoseconds, so billions of times a second. Every bit that's stored in your cache keeps going in a circle. Absolutely does. So we look for a more energy efficient way to do that. You're going to see a block in a second using spintronics and the other ways. So let's go back and see how these transistors work. So we're going to use them to access the cell. So I think you guys already saw this because I talked about the source, right? And drain is the channel, literally, for current to flow. And then we have a gate, which is the valve. And here is a 3-minute video to refresh our memory, because we're so into videos today.
The MOSFET controls the electrical current flowing between one contact, known as the source, and another known as the drain, by applying electrical voltage at a third terminal known as the gate. By modifying the electrical voltage applied to the gate, a conducting channel can be made to appear or disappear, allowing the device to be switched on or off. The MOSFET is manufactured in a silicon substrate, one of the most prolific materials in the Earth's crust. The advantages of using a semiconductor material are the following. Firstly, it can change its conduction capabilities by the controlled addition of impurity atoms.
You guys know the built-in process for rollers.
Secondly, it can have charged particles of different electrical signs, according to the type of impurity added. These particles are called electrons and holes. Electrons having a negative electrical charge, and holes having a positive charge. The final advantage is that in the same small piece of semiconductor, we can create regions with different types of impurity. If we manufacture a structure with regions alternating the two types of impurity, we can isolate the charges of one sign from charges of the opposite sign. Barriers between the regions appear, preventing the charge from flowing from one region to the other. In this situation, there is no electrical current. A similar phenomenon takes place when we want to move a liquid between two containers. Even if the containers were placed at different heights, the barrier would prevent the liquid from flowing between them.
As the
In order
high
to
potential
flow
energy,
between
low
the
potential
containers,
energy,
the
power
barrier must be lowered.
can't flow until
That's the
barrier.
role of the gate contact in the MOSFET, to lower the barrier.
It's
The
a
gate
barrier.
contact is
It's
made
not
by
barrier.
using a highly conductive material, separated from the
Iris.
semiconductor by an insulator. By applying a suitable voltage at the gate, the electrical charge can be attracted from the source. As a result, the barriers preventing the passage of the electrical charge are lowered, allowing the current to flow from the source to the drain. Under these conditions, the device behaves like a switch in its on state. If the voltage is not high enough to lower the barrier, there is no current, and the device behaves like a switch in its off state.
So if that's interesting to you, you can take Dr. Yuan's class or Dr. Sundram's class. We'll actually get into the, well, this is a P-type and N-type, but that's the next class. So we know enough that this is a voltage-controlled current switch. So we can switch the current in this channel by applying a voltage here, and actually very little current flows from gate into the channel because there's an insulating layer. There is a silicon oxide layer that's a very good insulator. So as you see in the read operation, somehow this should do right first. In the write operation, we're going to some of it's a bit that's out running around inside, but we're going to store a bit to begin. So we'll set which word we want to access, and then all the bits of that word have their own cell. That's going to activate the transistor to write this gate, to write the value into this from the input. And now this bit is running around it. And then we want to read it out. Read operation, we're going to activate the word line again. And we're going to activate the out to, well, word line is a selecting. It's a little bit confusing. There should be read and write handed together. But where speed is a concern, what's good about this is that this is simple switching. Basically, inverter is the simplest Boolean gate. This can be done in picosecond, the tens of picosecond order. There's no capacitors in here, which is dynamic ramps. So static ramps, you can say this looks very not static, but they call it static RAM because assuming that the power is turned on, that this does not need refresh. So dynamic RAM has capacitors. Capacitors always have some type of loss to the time constant. We're going to lose a stored charge, so that it needs to be refreshed. So in this design, static RAM, we say it's a 6T cell. There's actually 6 transistors. We say I only see 2. Well, there's 2 transistors that access the cell, and inside each inverter is 2 transistors. So he'll drew it when we were here, right?
Yeah.
So that's if you take CMOS with either Dr. Yuan or myself, we spend a month, seems like a lot, on this CMOS inverter, but we break it down. There's so many details, channel widths and ratios, and P-type and N-type, and one drives a 0 good, and it drives a 1 good, and blah, blah, blah. And that's the whole other course. For right now, just know that there's 2 transistors in each inverter. So there's a total of 6 transistors in an SRAM cell. So this was the. Let's look at some capacities of SRAM that are on chip. So actually, we're going to have logs soon. I'm not going to spend too much time on this for that reason, but let's jump over here. Before we see DRAM, which is a 1 transistor design, we can look at what our capacities are. If we have internet, maybe not. It's over. Maybe this is already here. Let's see. Yeah, good. Okay, so this is what I wanted to open. So this is a great thing. So we're at the end of the class now, almost, and a lot of these things were just numbers before. This should mean something to you. Clock rate, overclock multiplier. You can overclock it. You put this guy in the register. Socket is the number of pins on the chip. We passed a chip around the class. It's a pretty big chip. A lot of pins, 1150. Number of cores, 4. Here we see some cache sizes for L2 and L3. 1 megabytes, 8 gigabytes. What I wanted to show you in here is also, we talked about direct, map, set associative. You can see some of these happening at different, we see the split, remember split in unified cache. We can see this Pentium, this is the late, oh, actually it's just replaced. We have this 6th generation. But anyway, a month ago, this is the best, Intel's top of the line. It does have split L1 data and instruction, but L2 and L3 are unified. You can see set associative, and they're happy with 16-way, because for most programs, 16-way looks as if it's almost fully associative, because what does that mean? What is it? You have two-way cache, you have 2 ways. If you have collision, you have 2 ways to store the data. You have always store 2. So if this one's full, you have another place. Then you have bad luck again, right? Maps to the same. Remember, maps to the same set. The set is like a line. You have bad luck again and again and again. You have to have bad luck 16 times in a row before you have what type of miss? 3 types of misses. Or the 3 types of misses. It's a great study for the final. 3 types of misses. Compulsory. Yeah. Compulsory. I'll start with C. Compulsory. Just failed the final. They didn't fail the final. It's actually people. Compulsory, capacity, and conflict. So compulsory, we came to anything about with our mapping strategy. We can kind of prefetch, which is like a guessing game, but we don't cover that. That's the next class. But we had a way of addressing. The way of dealing with conflict misses was to add associativity. Capacity is just to make the cache bigger. That's the only thing you can do. But for conflict misses, we add associativity. So this gets rid of conflict misses pretty good. I mean, probably almost the same as fully associative, because the chance that a program has, and it's working. It's a working set. And its working set, it's the actual data that's currently using, is pretty low. That it has 16 instances of bad luck. Those things seem silly, but that's how I think of it, actually. But then I don't have to memorize anything, because it totally makes sense. So let's look at, you can click on this one and see some other technology. So let's look at doing better than static RAM for capacity. So static RAM is good for speed. Typical access time is less than a nanosecond. The problem is the cost per bit is very high, and it takes a lot of area on the chip, and it takes a lot of energy, okay, because those bits are always running around. So our other option for main memory, which we need gigabytes capacity, not megabytes, is to use dynamic RAM. Dynamic RAM is a different, what we call memory technology. Memory technology is a different circuit design. So a lot of smart people worked on these problems, and they're constantly trying to come up with new memory designs. We'll see this Spintronics one soon. So DRAM has the trade-off that even though it's slower, it has much higher density. So the density is better, the power dissipation is much less. The trade-off for this, besides being slower, is you have to refresh it. Refresh means 2% of the time, okay, about every 10 nanoseconds. How many hertz? 1.8, right? Oh, that's the easiest metric right over here. How many hertz is that?
10 minutes.
10, I'm sorry, milliseconds. 10 milliseconds is how many hertz?
Like 10 megahertz.
No. You're out. Okay, next one. 100? 100%. You're good for 1 point. Come see me. Oh, you said it first? Okay. Ali isn't good for 1 point. So, right, 1,000 milliseconds in 1 second is 1/100th of that. So it must be 100 times per second. 100 times per second is 100 hertz. You're good, right? Okay, so let's take a look at DRAM design. Here's DRAM design. You'll notice here is only one transistor. We call it one T cell. And the cool thing about this is it does really look like this. This is not too much frictionless plane. Blocks laying down frictionless plane. What we have is one transistor that's just to access the capacitor. Capacitor is storing the charge. Okay. So, how does a capacitor work? We took physics. Maybe you didn't take electrical engineering yet, but you took physics. So what's the idea behind a capacitor?
It pretty much like takes in the charge and for pretty much like it only stores the charge for like specific amount of time and like discharges it.
Yeah. So here's a capacitor, and I always think that these circuit diagrams and schematics, they look at like actually how it's built. You have two metal connect. We're electrical engineers, so we draw wires, right? These are long wires; they're metal plates. Okay. So what can happen here is if I instead put the voltage source the right way, what happens here? This is ground. Well, positive charge starts to accumulate in this plate. Why is it? It wants to flow to ground, but it can't because why? There's a gap. What's inside the gap is a dielectric. So negative accumulates on this plate. This is a dielectric that makes a capacitor. Well, I can store a 1 or a 0. Charge there, it's a 1. If I don't have charge, it's a 0. I can store it and I can read it back out later. That's the bit line. Either writing or reading. Okay. And we have that in the next slides. Operation. But while we're here, you'll notice that this has only one transistor per bit, plus a capacitor. We can make these fairly small. Okay. There's different dielectrics we like to use, but these actually can be really small, and the of this whole bit cell is small. The speed is very, very high. One problem, though, is the capacitor. We have time constant. Why do we have? Anybody? This is like. To me, once I realized it, even though so many books I never read it. Why do you have a time? Why does V here V sub C? Why does V sub C look like this? This is V, called Vs, so it's not going to be. Vs is a source, and this is T. And why is it like they say asymptotic, right? It keeps getting closer, but it never gets there. Why?
Difference of potential. As your
Okay.
the difference in potential between your capacitor and your voltage source.
Yeah. So initially,
It's 0, then it goes forward.
What we were saying is on the right track.
The potential difference between the voltage source and the capacitor is large in the beginning, but as you charge it up, it becomes lower and lower.
Why? Because like charges repel, right? Opposites attract, right? So when you start off with no charge here, this can rise very quickly, but then once, guess what? After like a certain period of time, this thing is already, the plates are already full. More charge wants to flow in because this thing wants it to flow there, but it also doesn't want to go because why?
Because there's no difference.
Because there's like charges repel, and that's all it is. So what happens here is we can't switch this too fast. We have to deal with this time constant. So it means that if this is a logic 1, maybe it's 1.2 volts, I have to wait till it gets at least to 1.0 volts before I say I've stored or read the value, right? Storing is the hard one. But static, I'm going to deal with it. Here we have a capacitor. Well, you're going to say, well, just get rid of that. Well, then you're going to use a lot of energy, a lot more space. So for main memory, which we don't access too much, we like the higher capacity. Remember the pyramid? But slower speed we can live with because we're going to leverage property of locality. So let's see operation of DRAM. Is this cool? DRAM operation. Is this what I said, right? We're going to insert the bit line because we're going to write a 1 or 0 here. It's grounded. Raise it to high voltage, which is not that high these days, 1 volt. And then we're going to turn this same MOSFET on and allow us to make a connection we want to write to where we're going to store it. And we have to wait 50 nanoseconds. After 50 nanoseconds, we have enough charge on here that we can turn off the source, and then the bit is stored there. But how long is it stored for? Well, only until the charge leaks off. How long is that? About 10 milliseconds. 10 milliseconds. Why does the charge leak off? Because that dielectric is not perfect. These are very close proximity, and there's also other kinds of losses. I said this in the other section today. That was one of my favorite classes, cool classes. Do you guys take electronics anymore in high school? They're always nobody, but anybody from here have a Mr. Yoder? Anybody have electronics? High school was an option, like a business. All right, see, I think the tax money and stuff is going good. I'm surprised. It's like how many years later? 30 something. You guys don't have. That was like the best class too, because the teacher was cool. He always like the Mr. Wizard guy. Yeah, he had a flat top, right? And weird glasses. He was like always zapping stuff. He was a radar guy. And he was like microwave. He turned his microwave oven, his waveguides and things. He would be heating up his lunch when he would go into class. Anyway, so the one day, that was the cool thing, is he had a Leyden jar. So what's a Leyden jar?
It's a capacitor.
It is a capacitor. So he had but it was sitting on the table. See, he didn't sit like this. This is a stupid way to sit. You don't have any fun stuff. So we used to sit at these lab benches, and we'd all sit around. There was a small class, but these parts there. He says, okay, what is that? And we play with it, and he says, what this thing is. He says, okay, let's pick one guy. He said, you're too much of a wise guy, so put it together. And he charged it up beforehand with the Van de Graaff generator. So the cool thing with the Leyden jar is you can take the metal. This is what he says. He says, if you want to send your friend, I'll make a joke. He says, you want to send your friend a shocking birthday gift. We're like, okay, what's that? And he said, well, earlier in the week of the birthday, you send them the outside metal plate of the Leyden jar, which is the jar, it's a container, just a piece of metal. Then you send them the nylon dielectric the next day. And then on their birthday, you send them the inside plate and instructions for assembly. So they get a shock. But actually, it's true. It will store the charge even if you take it apart. Of course, this is hundreds of thousands of volts, but very small current. But that's the weird thing about a Leyden jar. You can actually take it apart, even though it's set. Once you charge the dielectric, when you put it back together, you can still get some shock. He had many cool things. Like that was the first day of class. That was like when I got electrical electronics. The first day of class, he came in, and his jackknife is in the wall socket. So this is like electronics. Like you're thinking like he's going to teach you safety or whatever. No, it's like the opposite, right? He's like, what happens if you touch that?
It's going to
And he's like, I dare anybody to touch it. And of course, nobody stupid enough to touch it. He's like, well, why don't? Then he's like, he touched it. He's like, why didn't I get shot? Well, we don't know. Rubber shoes. And he said, I wore my rubber shoes today, but these actually are electrical insulated shoes. Some of his work shoes, if you're especially your construction guy, they sell you those ones. He says, don't try this with your own. Your bare feet, right? He's the guy that says with a capacitor, you have to leave $1. That's what we did back then. Just introduce capacitor too. You have to, everybody come in, you have to leave $1. It's like, leave class, you get $1 back. But that's like, between impedance and resistance, right? So resistance, he kept $1. So but impedance. All right, so we understand capacitor equal with DRAM. Capacitor is an easy concept if they explain it the right way. Mr. Harris, you're right with us today. So let's look at using DRAM inside the chip to receive DRAM as a module. We pass this around first day of class. This is a die inside each one of these chips. You can notice here, see any powers of 2? How many chips are here? 8. So there's a lot of ways we can organize this. Maybe we have each bit of the word here to store a byte. Remember, there's always byte addressable. Can you see the bits? Maybe. A lot of times we have 9, because we have parity. Parity is for error correction. And if we look inside, this is a cross section. So if we actually slice this and look sideways, you can actually see the different, remember the layers? Device technology. Scan electron microscope cross section. You can actually see different structures of the FET.